A very good afternoon to all of you. So, before beginning of this lecture is very important because in this lecture we are going to understand the difference between a continuous and a discrete signal. So, I will be dealing with various continuous and various discrete signals, and via that I will be clearing that what is the basic difference between a discrete and a continuous signal. Yes. Okay. Basically, continuity means that the system is having two things. It is continuous in time. Okay. Time, for example, on the x-axis. It is continuous in time. Again, I am telling you it is on the x-axis, and continuous in amplitude. It means along the y-axis. So, have a look at this signal. Yes. This is continuous in time as well as in amplitude. Are you getting it? This is continuous in time as well as in amplitude. But can we say the same thing for all the signals? There are various kind of signals that are present in this world. Yes, to be very frank, there are different kind of signals that are there, and we have to study each of them. Yes. So basically, the signals that we see in our day-to-day lives that are present right in front of us, that are there with us, those signals are nothing but, as we define them, those are analog signal or continuous signal. For example, a continuous current, it is going to be a continuous signal. Okay. Now, as the continuous current is quite clear, now I will definitely want all of us to understand that why the need of discretization occurs, why the discrete signals are important, why we have to discretize signals. Yes. Why the discrete signals are a necessity? Why? It is very simple. Discrete signals are a necessity because of the following points. First, very important point. Computers or the processors that we are using, these processors don't process continuous signals. Yes. These require discretized input for sure. Okay. So these devices will work on discretized signals or discrete signals. So now the role of A to D converters come into the picture. That a continuous signal, and that continuous signal in time as well as in amplitude arises on the horizon. Now have a look at this discrete signal. I want to shed the light that how a discretized signal is obtained, how we will discretize a continuous signal. So that will depend on the sampling, the ways in which we will sample these signals. For example, have a look at this. This is a signal f of t, and now we are taking samples of this signal. Okay, samples at equal intervals of time, at t equals to 1, 2, 3, 4, 5, 6. These are various intervals of time. 0, 1, 2, 3, 4, 5, 6. Clear? Now, what is the necessity of this discretization? Why discretization is required? It is very easy to understand, and we need to understand this thing. I had already explained this thing. Now, just a little bit of basics that is very important is that when we discretize a signal, whenever we discretize a signal, then we will observe one thing, and that one thing is that the discretized version may miss some important information. That's very important. If you discretize this signal at different instants of time, then you can easily observe that at some instants of time, suppose this part or this part or this part, these parts may be missed. These parts may be skipped. Okay, then what can we do? How can we cater to these parts? How can we be sure that the information is not lost? Yes, that is a very important thing. How can we be so sure that okay fine, the information is not at all lost? Okay, so needless to worry. There's simply no need to worry. It is very simple. Yes, we can very well and very easily understand this thing, that have a look at this signal. Again, I'm again emphasizing on the signal, that it is quite possible that some information is lost, but by following Nyquist sampling criteria. It means by forming the discrete signal from this continuous signal by applying the Nyquist criteria. Okay, then we can be very sure that all the necessary information is intact, is with us. I think I'm clear that all the necessary information is with us. Now I don't think that it is a big thing to worry, because as all the necessary information is with us, then it's quite easy, quite simple. So we can straight away proceed. Okay. Now, so I would definitely like to comment one more thing. That okay, the discretized version can be aliased or it can be very properly filtered. If aliasing is happening in a discrete signal, then for sure some data is lost. Now we can once again comment a very important thing, that a discrete signal will have samples at equal interval of time. Samples can be at a difference of 1, but the time period, the period of a discrete signal is going to be 1. 1, 2, 3, 4, 5, 6. So it is going to be 1. Okay, I think I am very clear till this point. So if we are going to put dn in the expression of sampled signal, then dn is going to be 1. Okay, now suppose this is a signal fn, 1, 2, again minus 1, 0, 1, 2, 3. Have a look at this. Minus 1, minus 2, 2, 2, 1. So we can very well say one thing, that fn is a discrete signal of time period 1 and it is a finite sequence. Now I would like to show some properties. For example, if fn minus 2 shifting is considered, so we will simply observe that how shifting is carried out on a discrete signal. Look at this. This is fn, and if fn minus 2 is asked, so we will shift the signal towards right. How the shifting will be done? For a kid's perspective, you can simply put fn minus 2 equals to 0, so n becomes equals to 2, n equals to 2. So shifting occurs 2 by a step of 2. But in which direction the shifting will be done? Either it will be in the positive direction, right side, or it will be in the left side. So we have to very clearly understand that in which direction the shifting is going to take place. I think I am clear now till this point. So the shifting will take place in the right direction by 2. Now have a look at this again. This is fn minus 2. This is n. 1, 1, 2, 3, 4, 5. So if the signal that's present at minus 1 will move by 2 towards the right direction. So this is a minus 1, this is 0, so it will come to minus 1, it will come to 1. So this 1 will be present at 1. Now this, have a look at this thing, 0. The signal that is present at n equals to 0 will move to n equals to 2. Okay. Similarly, the signal that is present at 1 will move to 3. The signal that is present at 2 will move to 4. Are you getting it? So in totality, I can say that whole of the signal has shifted by 2 in the right direction. One more property I would like to emphasize is scaling. How scaling is being done? Have a look at this f of n minus 2. This is the scaled. If f of n is this, then you have to do nothing. Simply divide this thing by 2. If scaling is done by 2, then all the x factors be divided by 2 and you will get the scaled version. I think till this point is very clear. I will see you in the next lecture. Till then,